So we've come out to the coast today to do some photogrammetry along the coastline. It's something I wanted to do for ages now. How cool is it going to be to print out this beautiful coastline, especially one with as much erosion? The cliffs have collapsed. It's going to turn out really interesting. I mean, just from the geomorphology of the site, I mean, the stratigraphy is really interesting, but that's neither here nor there. We'll get into it another time. It's going to be pretty sick. So yeah, let's just jump into it and see where it takes us. So a couple of people mentioned in my last video to give a little bit more of a detailed explanation of how you capture photogrammetry data. And in essence, it comes down to capturing as many photos as possible with as many angles as possible. Unlike doing a orthomosaic mission where you're interested in mainly a 2D flat plane image, you know, generating a map tile or something like that, our goal is to produce a model at the end of it. So you want to be able to capture as many angles as you possibly can, because that's the single most important thing. So the goal is to effectively do a linear flight path as we would with an ortho mission. We're going to do a crosshatch mission, and then we're going to be doing an orbital mission capturing 75-degree angle. And then, more importantly, we're going to fly down the coast here, looking back at the cliff face, capturing 45, 55, and 65-degree angles. And that should give us enough angles for Agisoft to be able to stitch together a really comprehensive little model that covers pretty much all our bases. We should have really nice terrain profiles. Awesome. You know, and the same goes for a digital elevation model that we're going to come out with. Now, the important caveat to mention here is the fact we're not using ground control points, so accuracy in terms of absolutes is not our goal. That will come down the line when we have enough money to actually get ourselves a GPS and we can start exploring more of the survey-related modeling missions that we're going to try and do. But for now, that's the goal. And at the end of it, we should be able to produce a pretty cool little ortho. So let's just get flying. So before we actually start flying, let's define what we're going to be flying in the first place. We've got a DJI Air 2S here, which I think is, even though it's a consumer level drone, is really good for mapping missions. DJI doesn't really make 1-inch full sensors anymore, so 20 megapixels with a 1-inch sensor is really good. Yes, you know, the enterprise level drones and even, you know, some of the small little mini drones have better camera systems, but this at least allows us, if we really wanted to, we could record in like 5.4K. Not necessary, but I think the image quality that this does produce is almost second to none, and it's still a fantastic little drone. I still use, even for work, you know, we still use the Phantom 4 RTK, which is also a 1-inch sensor and does a fantastic job with mapping missions. Archaic, yes, and even the Phantom series is a little bit like the Fisher-Price of drones nowadays, but this is a really comprehensive little drone, and I think it's going to be doing a fantastic little job. All right, so we're not going to be using any mission planning software in it here. I could use Drone Deploy, Drone Link, and they would work fantastically well. The only problem I've always had with those is that even though the Air 2S has its SDK released, and you can use it with those apps, Drone Deploy locks it behind a paywall. Drone Link, I haven't used it in the last year, but when I first tried to use it, some issues. The camera feed wasn't feeding, it was doing some weird things. Not the most impressed with it. And even at work, you know, I use Pilot 2 all the time to mission plan, and it's a great convenience. But do you need that to capture photogrammetry data? No, you don't. What you need to just be focused of and mindful of is the overlap between the photos you're capturing and what sort of data you're capturing to begin with, because that's all it really requires. And if you're looking at the logger itself and you're looking at your sort of Google map with your flight paths on it, you can guesstimate what sort of overlap you're going to be getting, what sort of data you are going to be capturing. And that's 9 times out of 10 is sufficient when you kind of gauge it accurately enough. And that comes from experience. But the important thing when you are flying it like that and flying manually is to at least have an observer with you. You know, you want to be a responsible drone pilot. All too often I've seen, you know, cowboy drone pilots who don't really care, you know, and don't look into your airspace restrictions, don't look into knowing that for certain types of drones, particularly like this one, you want to be registered. In my case, I've got both a GVC and an A2, and those are the things that I think are really necessary. Maybe not the GVC, but certainly your A2 if you want to bolster your competency here in the UK, where, you know, yes, you can get a flyer ID, yes, you can get an operator's ID, but the test is by no means, you know, the most comprehensive. An A2 does allow you to, well, fit into the A2 subcategory, as well as be able to just know the legislation around flying drones. Those are the most critical things that you need to be cognizant of. And, you know, we all want to be responsible drone pilots. We want to be able to fly and do a hobby and have fun with it, but you've got to know where you are and the people, restrictions, etc. around you, because those are really critical to be mindful of. So I've got an observer with me, my beautiful partner Ada, who's behind the camera at the moment. She's going to be, acting as the responsible observer here while I'm the pilot in command. We've set out a safe takeoff and landing space. We've got a little bit of emergency procedure in place, and those are important. Have all of those things ticked off and in mind when you are flying a mission like this, just in case things go wrong. And yeah, that's all it takes half the time. Just be mindful. So let's capture some data.
Llegaste de la nada, cuando menos lo esperaba. Al encontrar tu mirada, ya estaba perdida. Con tu forma de hablar, sin miedo de expresar. Fuego al cantar, ya sabía. Esto tenía que pasar, de pronto todo en su lugar. Había dejado de buscar cuando aparecí.
All right, so we've finished flying our mission here. We've captured as much data as humanly possible. From multiple different angles, covered all our bases. We're going to get back, process this data, and see how it turns out, because I think it's going to be an interesting model. The cliffs are really interesting. The terrain profile is going to be really interesting. I'm as giddy as can be, and yeah, we're going to see how this turns out. So let's get back and do it. So we've made it back to my spare bedroom, and we're going to process some data. A couple of people asked in my last couple of videos to give a little bit more of an in-depth guide on how to actually process the photogrammetry data, as well as get it ready for 3D printing. So in the first instance, we're going to jump into Agisoft, process the data, get the model ready, export it, get it into Blender, and yeah, then go through the Blender workflow, which I should preface this by saying that I'm by no means an expert when it comes to Blender. There are loads of great tutorials and guides out there, but and I've followed a couple of them, but as with most things, you kind of just figure it out as you go, and the workflow I've come up with is, well, it works. It works for me. It's, there's probably a million ways to do it and probably a bunch of better ways to do it, and I'm certainly keen to learn more and find out more, so if you've got any ideas or suggestions, pop them in the comments below. But yeah, without further ado, let's jump into processing this data and just kind of go through it. So first things first, getting the photos in Agisoft. Here we go. So we've got all our images added into Agisoft here, and we've checked the image quality, which is an often overlooked but incredibly vital step to do. We're looking for a number between, say, 0.7 and 0.9. Anything closer to 1 indicates a really nice, crisp, clear image, and that's effectively what we're after. So we know we're dealing from the get-go with a fairly good data set. I'm chuffed to bits with that. So we can go ahead and align our photos. So just to go through a couple of the settings here, yes, some of these are the stock settings, but we can go through what they are and effectively what they do. So first off, we've got generic pre-selection. And effectively, that just automatically checks the image content and skips non-overlapping photos. So yeah, it saves time by ignoring obvious mismatches between images. We've got reference pre-selection, so that uses camera location data, orientation data, things like that, to skip non-overlapping shots. So it's great for large data sets, but only if your position data is accurate in the first place, which in this case it is. DJI's sort of geotagging is incredibly good. We've got the two most critical, I think, which is your key point limit and your tie point limits. The key point limit is the max number of features or key points that are detected per image. So higher limits can capture more detail, but it can also increase your processing time. So if you've got a fairly weak and pathetic little system, I would stick around the 40,000 mark for good measure. We have our tie point limit, equally as important, which defines the max number of match points or tie points retained after feature matching. So, higher limits in this regard can improve model accuracy again, but again, slow things down and will chow your RAM to no end. So avoid, going ridiculous with these numbers. Anywhere between sort of 4,000 and 8,000 for your tie points, and say 40 to 120,000, with 120 genuinely being on quite the high end. 40,000 and 4,000, is a good range to sort of stick around. I always include the stationary tie points, so that sort of filters out points that appear in nearly the same place in all images, and it adds little to the 3D info that you're trying to get. So it prevents ghost points and can improve alignment quality. Then we've got guided image matching, which certainly for drone or aerial photogrammetry is certainly quite useful. It uses the approximate camera poses to guide the matching, so it can speed up alignment if you have really good camera reference data. In this case, we're not going to enable it. We don't necessarily need it. And lastly, we've got adaptive camera model fitting, another really important one. So that automatically refines the camera parameters like distortion based on the data itself. So usually it yields better accuracy unless you already have perfect calibration to begin with. So that sort of goes through the process. We can click OK and begin the alignment. All right, so we've got our sparse cloud processed here, and as you can see, it's looking pretty good. Yes, there are some floaters that we can see, certainly where the water was, and erroneous points floating in space, which is certainly not a good thing, but is why we're going to jump into our next step, which is cleaning our sparse cloud. Before we do that, we can just kind of have a look at our cameras here, and you can get a guide of how I've sort of captured this data. I did this orbital mission to see how much value it really added to my mission. I think we could have gotten away with it if we just stuck with the oblique shots that we took down the coast here. But for the most part, I'm very happy with how this is looking. What we're going to do next, though, you need to prepare yourself for, because I remember when I first jumped into Agisoft and I was cleaning data, certainly the sparse cloud, and I was being taught by someone, and I was like, I seem to be deleting a lot of points here. Is that really going to be a massive issue? It can be, but you got to trust the process. So without further ado, let's jump into cleaning it. So we're going to go to gradual selection here, and we've got a number of options. So we've got reprojection error, reconstruction uncertainty, image count, and projection accuracy. So there's three that are really critical. So reprojection error is the first one, and effectively that measures how far each tie point's reprojected position is from the actual detected feature in each photo. So high values indicate the point doesn't match well across images, and often it's an outlier. So, the use case would be sort of removing points with large reprojection errors to help ensure that, the overall accuracy of our final output is going to be, pretty good. We have reconstruction uncertainty, so another critical one, which is it estimates how precisely a tie point is defined in 3D space itself. So that's based on camera geometry or multiple viewing angles, things like that. So high values in this case sort of indicate that the point's 3D location it's not particularly well constrained, usually due to limited or poor overlap between our images themselves. So filtering high uncertainty points improves the reliability of the model itself. Image count, not the most important. Don't get me wrong; it's useful in certain scenarios, but it shows how many photos observe a particular point. So low values indicate a point is seen in very few images, which can make it look a little bit less robust. So removing points seen by only say one or two cameras can eliminate weak matches or noise. So it can be quite useful. I seldom delve into sort of image counts, but you can do. Projection accuracy, however, certainly very important. So it reflects how confidently Agisoft can pinpoint the tie point's 2D location within each image. So it breaks down to sort of pixel levels of accuracy here. Low accuracy indicates, a potentially blurred image or ambiguous feature matches. So filtering out those low accuracy points can tighten up the overall alignment. Typically you'll use these gradual selection criteria in a sequence. That is quite important. Starting with reconstruction uncertainty, then projection accuracy, and you're finally going to reprojection error. To iteratively refine your tie point cloud. So the level slide or the value sort of sets the threshold. Higher or lower values decide how more aggressively you're going to be filtering. So without further ado, let's jump into processing this. So we're going to go to reconstruction uncertainty. I typically like to use a number around 12, and as you can see, it selects quite a few points. Now, this is what I mean when I say, prepare yourselves mentally, because these points we want to get rid of. We don't really want them. So we will get rid of those points. And after you delete these points, it's really important to go back to do your adaptive camera model fitting again and just run it. So for every step that we're going to do, we're just going to run the camera model fitting each time. So again, back to it. And we're going to jump into projection accuracy. I like to have a number about 10. It's not going to select that many, but it will select, you can see here, it selects the outliers that we've got, in the ocean, etc., floating in space and not really tied to anything in particular. So we can go ahead and get rid of those. And once again, adaptive camera model fitting, run the process, and finally we can get to our reprojection error. So we want to have a value. This is also going to make you cringe a bit, but 0.5. So 0.5, quite important. It's a nice low value. It indicates where there might potentially be, a few outliers that we don't really need to worry too much about. So go ahead and get rid of those. And don't get too scared by what you see here, because we've still got a lot of points. This is not going to indicate, what the actual dense cloud that we're going to create, or indeed, the digital elevation data or the model that we're going to build when we start to build up the mesh and texture, things like that. So I'm happy with how clean this is actually looking right now. I think it's going to produce a pretty nice model. So yeah, and there's no sort of floaters just chilling out. We're okay. Everything is consistent, and that's effectively what we're looking for. We're looking for consistency. We're looking for points that we know should kind of line up. You don't want to have points too high, too low, etc. Just kind of in the middle there. Happy days. So yeah, we can now build our dense cloud, and this is certainly the most intensive process of photogrammetry itself. When you're building your dense cloud, it uses a lot of system resources. If you've got a professional graphics card, even a just a gaming graphics card, it's going to help you, and you want to be able to set it to be able to utilize that. And it takes a while, depending on how you want to process this dense cloud. I usually typically keep it at high, and when it comes to depth filtering, I choose aggressive. So having it be aggressive removes the outliers, but it also may remove some details. So it results in a smoother but potentially less detailed reconstruction. So depending on what sort of data set you're trying to capture, you might want to go with an option that is more sort of mild or moderate, so that retains more detail, but it can also include way more noise. So I usually, choose aggressive to do this. So yeah, we can go ahead and go grab a coffee and we'll reconvene. Okay, so we finished processing our data here, and we're about ready to view the dense cloud. Before you do, though, and it's a crucial and often overlooked little step sometimes, is to save your work specifically at this point, because when you view the dense cloud, sometimes your PC can freak out and suddenly you lost your progress. For particularly large data sets, that's hours of work down the drain. I've done it before. I've got way too excited. I just want to view things, and I'm an idiot sometimes. Don't save my work, and I've got my head in my hands going, what have I done to myself? And it is just an important sort of tip regardless. At every single stage, when you add the photos in, save the project. When you align the photos, save it, as something incrementally, as something different. When you, build the dense cloud, save it as different, and go through the process, be it, building the DEM, building the mesh, the textures, etc. You want to be able to at least go back to your workflow, if you want to, for no other reason other than, if you want to try something different, or something's gone wrong or seriously awry, you at least have a way back, a path to find yourself once again. So without further ado, let's view the dense cloud. Here she is. It looks good. It looks really good. Yes, there are some outliers here, but we're still going to do some cleaning on it. But I'm pretty I'm pretty happy with that. I think it looks really good. Let's just do that quickly. I don't know what's going on, but it looks really good. Yes, granted, the peripheries of the site certainly aren't the best. I get attached to the peripheries of my data. We can't do much with that, but that's not part of the model I'm trying to create in the first place. So I'm not too concerned. And yes, we could just delete those and sort of create a really nice static sort of image, flat image, fine. But we can also use a polygon later, set it as a boundary, and then when we export our model, it's going to clip to those boundary edges. So again, I'm not too concerned. Yes, you can clean things up, etc. And depending on what sort of model you are making, you might want to create some mask layers. And that way you can exclude different parts of the background, specifically if you're looking at like static objects, whatever whatever it is. So in our case, not too concerned. It is what it is. So we're going to go and we're going to filter by confidence. Now, when you're filtering by confidence, it lets you selectively remove or isolate points in the dense cloud that are based on their confidence values. So each point in the dense cloud has a numerical confidence score, typically between 0 and 255, indicating how reliably Metashape thinks that the point was reconstructed in the first place. So high confidence scores, those closer to that max value there, 255, it indicates that the point was observed and matched consistently from multiple angles. A low confidence score, closer to 0, the min score, indicates the point may be, noisily or only partially matched, or, is poorly supported by the images themselves. So by filtering out points below a certain confidence threshold, you can clean up stray or low quality points and, well, leave a denser cloud of more reliable geometry. Let's go with that. So in our case, we want to set a min value of 0, and between 1 and 2, I think is fairly reliable. In our case, I'm going to go with 2, just because I think there's going to be, certainly with this by the shoreline here, it's going to be a little bit exciting, but I think this will be able to get rid of most of the points we want. So in this sense, I'm isolating only the very lowest confidence points in the dense cloud, so it's those points that I want to remove / examine more closely. So here we go, and you can see it's selected quite a lot. Again, most of which is around the peripheries, and yes, on the shoreline, and it's picked up these points here. We kind of just want to get rid of them. So, and you're freaking out. What happened to my model? So we can, don't worry about it. Go back to reset your filter, and there we go. So we've cleaned up. We haven't lost anything when it comes to the cliffs that we're actually interested in. We've gotten rid of a lot of the stray points that we're not too concerned about. So yeah, I'm fairly happy with how this is looking, and we can move on to our next step. So we're ready now to jump to our next step, which is going to be building the mesh itself. I usually like to generate the DEM and ortho imagery before I ever jump into building mesh and textures, things like that. And that's just from a work point of view. In large civil engineering projects where a lot of the aerial survey data that we deal with is ortho imagery and it is DEM data. Particularly when we pop it into GIS platforms and we, certainly from the DEM data, start extracting topographic information from that. We do volumetrics. It's super interesting and super cool. It's what got me into my love for survey in general, certainly for photogrammetry and remote sensing. For stakeholders, for decision makers, being able to actually see a site unfold on a sort of week by week basis. Satellite imagery can only take you so far, and certainly not to the resolution that you can get when it comes to ortho imagery in general. So really powerful tools. And I've generated the DM data, and sometimes when you're dealing with ortho imagery, a lot of the detail, certainly the terrain detail, gets lost in translation, and you end up sort of struggling to really get a sense of the topography of the lay of the land, so to speak. And this way, yes, you can really start to see subtle earth features. And that to me is just the coolest thing in the world. But we could jump down that rabbit hole and descend into chaos, and we will not do that. So we're going to be building our mesh, and we've got a couple of options here. And I usually like to, for my source data, do it from the dense cloud. That's kind of the industry standard for the most part. Yeah, you do have a couple of options, and certainly when it comes to you can use the depth maps. Building directly from the depth map can sometimes produce very detailed results, especially in the latest versions of Agisoft. But truth be told, you won't have the flexibility of say manually editing or classifying the dense clouds before you actually get to the point of where we are now of creating this mesh. So for us right now, building it from the dense cloud, that's what we're going to choose. For surface type, arbitrary 3D. It's best for full 3D objects that can handle sort of complex geometry from all sides. It's high contrast height fields is more suitable for terrain-like surfaces without like undercutting features, things like that. Our face count, we're going to be choosing high. And as you can see there, 6.5 million. It's pretty intense. So it roughly controls the mesh detail itself. So higher quality, more precise, but leads to more processing time. For interpolation, obviously we're going to leave that enabled. That allows it to fill small gaps, holes in the mesh, based on sort of surrounding data. If you disable it, it's going to leave holes where data is missing, and sometimes that can be important. Certainly when you don't want it to kind of generate any data where there was none. And you can also choose an extrapolated. Now extrapolated tries to fill larger gaps by guessing geometry beyond the available data. That really is, it's in the name. It's extrapolated. It's making it up. So yeah, we're not going to worry about that. So we're going to enable calculate vertex colors. So that adds per vertex color information to the mesh. So it's less detailed than a separate texture, but useful for certainly for quick visualization, or if we later down, if we're going to skip texture building altogether, which we're not, but keep it enabled. So yeah, we're going to hit process and see where it takes us. So now that we've processed the mesh, we can kind of interrogate it a little bit. In this case, we can view the solid model, and this gives a good indication of what it's going to look like when we actually go to 3D print. This is more of an indication of what we want as our end result, really. Our next step from here is to build the texture on top of that, to create a colorized model. And that's going to be really important if we want to create 3D scenes, or when we want to do photogrammetry on static objects, be it like an archaeological artifact, something from my past, which is going to be really cool, but really important to have really good texture data associated with that. So we're going to jump into that. So we can build our texture, and we've got a number of options here. And for texture type, I usually select the diffuse maps. Plain and simply because it creates a standard color, the diffuse texture for the 3D model. For the source data, I typically choose the images, even though we've used the calculating vertex colors, and that would be if we chose the 3D. Now, when you choose 3D model as the source data for building the texture, Agisoft uses the existing color information stored in the mesh vertices that we created to generate the texture, rather than projecting the color directly from the original photographs. Now, this can be really useful if you've already baked the colors into the mesh, as we have, and just want a texture file of exactly those colors. But for the best texture quality overall, and certainly the most accurate, you want to use the original photos. This way, Agisoft reprojects color from the full resolution onto the mesh, which again, just typically yields a sharper and more detailed texture. For our mapping mode, we're going to choose generic, so that automatically generates a UV map suitable for general 3D objects, not strictly for your sort of flat terrain or terrain-like. Our blending mode, we're going to choose mosaic. So again, that blends the overlapping images, or at least the areas, as smoothly as possible, correcting things like brightness and differences between the photos themselves. The texture size. So, this is obviously going to set the resolution of the texture. In this case, sort of 8,192 by 8K. So this is going to be really high resolution, and the count itself sort of refers to how many separate texture files Metashape is going to create. So one indicates it's going to create a single texture map. We will sort of enable ghosting filter. We're not going to enable hole filling, but yeah, that's where we're at. So let's get processing. So there we go. We have processed the texture, and look at that. It's looking awesome. It's looking incredible. This is where the power of photogrammetry truly shines, because when you're looking at a model that has just worked and come together, like that whole scene there, just that is just so cool. The trash on the beach, even the sort of texture that's of the cobble beach here, it looks awesome. It looks really fantastic, and this is the power of, this is where photogrammetry truly shines. Being able to just kind of interrogate a scene and see what you're looking at. That is the name of the game. And it obviously it's a process. It takes a lot of time to get it to this point, but the results are super rewarding. And it starts with really good data capture in the first instance. And what I mean by that isn't necessarily having the most perfect flight paths. As you can see from mine, yes, without mission planning and on a windy day, things get blown out of course. Did my best to remain as consistent as I could be. And that's what it takes, and capturing a lot of data from a lot of different angles. You can see there, I've done my due diligence on the amount of photos taken, and the consistency in terms of levels, in terms of angles, in terms of placement, to keep it as consistent as possible. And the net result is a really, really good image. So you don't need the mission planning software. You don't need to have the most comprehensive or advanced drone, let's say, like an enterprise level drone, or even the latest drones. You could do and achieve very similar results with a DJI mini drone. Yes, the sort of ground sampling distance won't necessarily be the best, but you're still going to get really fantastic results. And Agisoft, I've got a license for Agisoft Metashape Professional. This is largely through work, but you know, they do offer trials, and even with the standard version, you can process, you know, really comprehensive models with that. You know, there isn't a hell of a lot of functionality apart from, you know, at least if you want to put in laser scanning data sets, or you want to start meddling with the sort of the console itself, things like that, you know, a professional version starts to come into play. But this is, you know, there are a lot of avenues to be able to get into photogrammetry, and I still think, yes, there are a lot of really awesome, you know, photogrammetry softwares out there, be it Pix4D, be it SiteScan, be it even Drone Deploy. You know, they all offer various functionality, but some of them, you know, certainly the cloud-based processing like your Drone Deploys or SiteScan, they I don't like that they take control away from you. You know, the Agisoft is one of the last vestiges of really being able to get into your data, clean your data, see your data, really manipulate, what you want from it. And you know, if you go down that route, I recommend going for Agisoft above most others. Yes, you can get really good results with AI processing and things like that, but you know, part of the joy is also just learning what works with photogrammetry. When you're processing the data, when you're interrogating your own data that you've captured, be it from a DSLR camera, be it from a drone, whatever it is, you really get a better sense of what you're actually capturing, how you're capturing it, what matters in terms of processing, things like that. Those are critical. So there we go. We have a model. We have a really cool textured model. So what we're going to do now is export this as an OBJ file and get it off into Blender. But before we do, we want to define our boundaries. So if we go here into our sort of DEM, our top-down view, and switch over to draw a polygon, we want, you know, effectively just kind of straight edges on the peripheries of our model here. So at least it's going to be, we'll do a little bit of cleaning up regardless in Blender, and there's, you know, a couple of ways to do that. A simple one, which is the one we're going to use. But you know, first and foremost, let's just effectively define the sort of boundary that we want. And if we kind of do something like this, not worrying too much about, you know, the accuracy of it, you can get down, because all of this is going to be clipped out, everything beyond that. And I kind of like the way that looks, to be honest with you. So we will just link that up and get it out, select it, and then set the boundary type and set that to our outer boundary. So we're just going to effectively cut out this little portion in the middle here. So we're going to hop off into Blender now and have a look at the model. So we've got our model imported here into Blender, and it's looking awesome. It's come out way better than I thought. It's so cool. I mean, the texture of it just looks fantastic. Printing a eroded coastline, it just looks cool. And you know, as great as it is, if you sort of go to the side, however, it will highlight one very critical problem, certainly when you're working with photogrammetry data, and certainly with Agisoft. You know, if you try, because Agisoft does allow you to export as an STL file, you know, native to 3D printing. The problem, however, is that if you exported this as an STL and put it into your slicing software, it would not do anything. It would not slice. You'd get all errors, and you know, no one wants that. So we need to build up some volume to this. We need to build up a base. But before we do, we can also interrogate, or at least showcase, why we built texture, and you know, why we exported as an OBJ file. Yes, there are certainly FBX files, file types, you know, where some of the texture is integrated. We're not going to worry about that right now. But OBJ files, we also get an MTL file and a JPEG file that contains all of our texture information. So if we go over here to you know, sort of shading, look at that. Look how awesome that is. Look at how it's photorealistic and it's cool. And it highlights, you know, one of the huge benefits when it comes to photogrammetry, and that is, you know, being able to reproduce those photorealistic scenes. You know, something like Microsoft Flight Simulator, for instance, relied heavily on this sort of process of photogrammetry to reproduce environments because of how it's so comprehensive. It's cheap, to be honest with you. I mean, it's a lot cheaper than in sort of investing in high-end laser scanning equipment and things like that, LiDAR equipment, which would certainly give you, in terms of absolute accuracies, better results. But using CMOS sensors from drones, capturing this sort of data, or from satellite data, from flying around in an old Cessna, something I did at university. This is, it's just so awesome. This to me just gets me about as excited as you can be about a model. Let's get back to what we're doing now, which is building a base for our model. So if we quickly head into edit mode, first thing we want to check is that we select any floating blobs that might have been missed from our cleanup in Agisoft, because when it comes to 3D printing, if you've just got a blob in the air, yes, it'll try and print it. Sometimes you'll get shown up errors, etc. But it can ruin your day and ruin a print. So you want to get rid of a lot of that guff before you do so. So I mean, sometimes especially those originating from photogrammetry 3D scans, or complex CAD imports, come with small disconnected patches of geometry, and these floaters aren't attached to the main body of our model itself. So in a slicing program, these detached pieces, they cause unpredictable results, as I say. So we want to avoid that. So to test for that, we're gonna select linked. So you can just press L on your keyboard, and that'll select everything. And then we're going to invert that selection to, select everything that is not connected to the main body of the model. So if we Control I. As we can see here, we don't actually have that issue. Where we made our polygon, we got rid of a lot of the guff that was on the peripheries, which is where a lot of our issues originated from. We did a really good job of cleaning our data to begin with, to make sure that we didn't have those floating points. And this is a really good indication, a good sanity check of how well you've done at cleaning the data. In our case, I think we've done a pretty stellar job at cleaning the data. So next step, we want to give it some volume. So what we're going to do is we're going to extrude it. There's probably a lot of ways to do it. I think the easiest way that I know how is just to extrude it and to extrude the face of it. And we're going to do quite a bit, because we're going to cut it in a second. So we've got the model extruded. As you can see, it's got some volume now. It doesn't look like a wafer piece of paper, which is fantastic. The problem is, obviously, it's an exact negative of our surface here. So we're going to do a couple of things to rectify that. Slice it off at the bottom and get it to print in this sort of easiest way, because we want to preserve. We don't want to play too much around with the orientation, because this right here gives us what the lay of the land actually is. This is going to be, once it's sliced at the bottom, it's going to be a very accurate sort of terrain model. And that's what we want at the end of it. That's kind of the point of this. So first things first, though, we need to also check that our model is manifold. So effectively, non-manifold describes edges or faces that don't form properly closed surfaces, so holes or edges shared by more than two faces. For 3D printing in general, it expects watertight models. So if your model has, sort of non-manifold edges, it creates slicing errors, leading to failed prints or missing sections when it does slice, which is no bueno, no good. So we want to avoid that a little bit. So the best plugin to get for Blender is the 3D printing plugin, because it's very simple. Once you've got your model selected, you can effectively just click it, make manifold, and off you go. So now that we've run the make manifold command with the plugin, we can go into edit mode once again, and we can select and go select by trait, and then select non-manifold. And just kind of double check. So if anything's highlighted here, it's a non-manifold edge. In this case, we're good. We know we have a watertight little model here which is fantastic. The next step that we can sometimes do, in this case, we're not going to do it because, just from, you can inspect this essentially by going through the process of, once you've extruded and checked for non-manifold edges, you can see, whether or not the model itself is looking weird, and you certainly, in terms of its triangulated mesh, whether or not you're going to have weird holes, or certainly if you've got duplicates that might be in the same spot and causing weird geometry errors or something like that, overlapping vertices, which can cause weird geometry errors or weird shading artifacts, something along those lines. But if that were the case, you can go back into your edit mode. Once you select all and then go back to your mesh and then start to clean up, you can start to merge by distance or fill holes. These two options are the first that I usually go to. In this case, we're not going to do that. It's just not necessary right now. What we are going to do, though, is we're going to run our Boolean operation. So effectively, a Boolean modifier lets you combine or subtract objects from one another using operations like union, intersection, or difference. So again, it's the most easy, straightforward way to slice up your model. Yes, you can use the knife tool, but I've had weird hit and miss errors with it, so it's easier just to kind of treat it like one object, big object, slice it and move on. And in this case, for most, and it's the reason I haven't deleted my little cube down here, is because we're going to scale this cube and effectively make a massive cube that sits underneath our model. It can be quite resource intensive, but we're gonna deal with that. I mean, that's just way too big, to be honest with you. We can modify that a little bit to make it a little bit smaller, and just so it can sit underneath our model. So that's looking pretty good. We can move it up where it sort of intersects the middle, and then scale its thickness, and just get it to a nice thickness. Ignore what I said there. So yeah, that's pretty good. So yeah, we've got that in place. What we want to do, and it can sometimes affect how the modifier actually works, is just to go in and select all transformations. So if you go Control A and then go all transformations, it'll revert everything back to normal. So here we go. You can see that in terms of its scaling, it's all off. So we want to reset all of those transformations, for both the cube and for the object itself. Just reset them all. So then we're going to select our model. We're going to go over here to modifiers. We're going to add a modifier. We're going to search for the Boolean operation. We're going to use the little dropper, and we're just going to select the cube. This is where things get a little bit exciting. A little bit exciting because, as just happened, it freaks out, and it's like a weird, very resource intensive little kick. But I can really tell you we're in a good place, because as soon as we get rid of that cube, boom, we now have some depth and base to our model, which is sliced in the right way, which is that's exactly what we wanted. We wanted that to give our model a base. And so I'm happy with that, how that's turned out. We're going to do one more, which is to choose. I'm going to do this end, and I'm actually going to do another modifying operation on this side, to just get rid of, to make a nice flat surface to print from, because I'm going to print it vertically. If we printed it in this orientation, obviously, if you think about how a 3D printer is going to build up layer by layer by layer by layer, printing in this orientation, we're going to lose a lot of detail on our top surfaces. That's just the nature of it. It can't sort of work its way around complex geometry from the top. So if printing it vertically at least allows it, to print in this orientation, so that every line allows us to actually get in all of this detail. It's easier for the printer to print that way. That's the simplest way to sort of go about explaining that. So let's add in just another cube, and we'll scale that one in much the same way, but we'll just get it placed on the side. So there we go. We've run the other operation. We can get rid of our other cube, and we've got a nice base to print from. So we'll print on this this will be on the build surface, and we'll print it up sort of vertically. Not sure how that's really going to turn out, but I believe, I have hope. So we're going to export this as is. This is now ready to 3D print. There it is. There is our model for 3D printing. So let's get over to Creality Print and get this sliced up. So here we go. We've got the model into Creality Print, and it's pretty much ready to go. I made a few minor adjustments. I ended up performing another Boolean operation on both sides as well as the back, just to kind of make it look a little bit neater. And I got to say, I mean, look how awesome that really looks. I'm so excited to see how this actually turns out. It's going to be a little bit of a challenge, and it's going to be a challenge because, as I say, like when it actually comes to, if we 3D printed it in this orientation, and if I just kind of change the slicing just a bit, and we scale it just a little bit down, just to get it within the confines and slice it. I'll show you what I mean when I say like it's not going to come out as we hope it will come out. And that's largely because of the way that FDM 3D printers actually work. You can see here that there are a lot of top surfaces. So when it gets to the top surface, we're gonna come into issues that where effectively small horizontal areas that might show it's going to show layer artifacts. It's going to, we're going to lose all of our terrain detail, things like that. So it's just not going to be good. Yes, if we look at it from the side, some of it's going to look pretty interesting, some of it's going to look cool, but that's not why we went through all the rigmarole to try and get a kind of half-assed 3D print. I mean, it would look cool, but it wouldn't be accurate to what we're doing. Yes, you're probably going to get better results if you used a resin printer, but we don't have a resin printer, and nor do I want to venture down resin printing too much. In my little flat, it would be a nightmare. So we're going to do what we can to get the best results, and I think the best results are definitely going to be to print this vertically. So we're gonna orientate this quickly. So there we go. We've got it orientated vertically. That way, it's going to obviously build up all the texture as it goes up, and I think it's actually going to turn out pretty damn cool. I mean, this is it's a high resolution model. It's a good looking model. Yes. Is it perfect? Not really. Obviously we've got some blobs and things that are over here that I'm not too pleased about and probably aren't going to print too well. But for all intents and purposes, this is a really cool looking model. And if you look at the beach, it looks so cool. I'm almost at a loss for words, to be honest with you, just by looking at it, because I'm so excited to see how this is going to turn out, and we're gonna print it at 0.08. I do have a 0.2 millimeter nozzle. I haven't put it on. I don't think we really need it. We're going to see how this turns out. I might switch over to the 0.2, and maybe we'll do that for a second round of printing. We'll see how this goes. So let's jump into some of the slicing. I'm going to print the first layer at 0.22. I just think that's going to be a little bit better. The seam position, another one, we're going to place that to the back so we don't actually have any
seams facing towards us. In terms of wall loops, we only need 2. I mean, this is not a structural print. We can go higher, not really necessary. Don't want to go lower. For the top surface, we'll just keep things as default. Again, our top surface in this case is almost irrelevant. The infill, though, I maybe 10% infill. Using sort of gyroid. I quite like gyroid above anything else, to be honest with you. I think it helps retain a little bit of consistency within the model. I sometimes find with grid or anything like that it can pull in the model. So we'll avoid that. Gyroid, I think will be fine. Pretty much everything else, we don't need to worry about. I'm printing this at fairly stock speeds here. Not going to be changing anything. The only thing I will change that I'm going to be using a Erosion matte PLA. So I've set up a profile for this, which is fairly consistent for high speed prints. I did a lot of the calibration for some of these profiles in Orca, and then just kind of transferred things over to this to see how it goes. So as you can see, not the most comprehensive or complicated process to slice this model. And let's just slice it up and get back to it. And there you go. I mean, just looking at that, it really looks about 10 billion times better than it did before. And you can see how it's actually going to print, where those layer lines are, and how it's going to preserve detail, which is the most important for us with something like this. I think something like that, if we can achieve anything that vaguely looks like that, we have won. We have won. And I'm really looking forward to seeing how this prints. So yeah, without further ado, let's send this to the printer, and we'll print a calibration for this because I'm just a little concerned. So we'll, even though I'm not convinced it really does anything, but we want to level the bed regardless. It's going to be about a 5-hour print, let's say, which is fairly long, but we're at very high resolution here. It's not the craziest amount, and yeah, we're gonna see how this goes. So let's start the print.
So if you've made it this far in the video, I mean, good on you, because it's been a long one. But it's been one of the funnest little projects that I've worked on in a very long time. Photogrammetry and remote sensing, as well as 3D printing, are some of my biggest passions in life. And you know, this project has been it's been awesome. And so I hope that you sort of gained something from it, you know, at least, you know, from the initial, you know, how to capture data in the first place, the sort of camera angles you need, the sort of mission planning that you can do without, well, bespoke mission planning software, to getting the data into Agisoft and processing it, and you know, getting that ready for Blender, going through Blender, getting into slicing software, and ending up with a 3D print. Now, again, I'm no expert when it comes to Blender. The workflow I've come up with, it works, it's functional, it's, you know, I think it's great. But obviously, there's bound to be, you know, numerous ways to do it and better ways. So, and if you do have a better way, let me know. But for the time being, you know, I think we're in a good place. We've managed to print the coastline. And as you will note, we actually have two prints. If you'll recall, we initially printed it in this orientation, you know, sort of going up in layers like that, because again, if we printed it like that, you know, everything's a bit of a top surface, it doesn't look too good. So we printed it like this, and you know, it came out really, really well. It looks cool. I mean, sort of, as you go down the coastline and start to look at things, it looks awesome. I mean, the detail and the resolution, it looks, it's cool. I mean, I'm almost lost for words just kind of looking at it and going, oh, that actually turned out way better than I expected. And once we had printed it and I'd looked at it, and yeah, then it dawned upon me that, you know, going through all the Boolean operations that we did on the sides and the back, you know, we actually could have just printed it in this orientation, and you know, built it up going, you know, sort of layer like that. Does it look better? I think it looks a little bit better. I think you know, when you're looking at it head on, and you know, the layer lines are less distinct. You know, the only problem is, you know, is that there is some jaggedness, you know, certainly on the coastline and on the ridge line, you know, where on sort of the cliff by the path. You know, it is a little bit more jaggedy, and that's just because, you know, it's effectively a top surface, and you know, where you've got seam lines, it's a little bit more difficult to hide those seam lines. So it's a little bit more noticeable, but I think the result is a little bit more, you know, sort of cohesive. It looks cooler. I just think it's a little bit better. But you know, the two of them I think are fantastic regardless. I think both models have actually come out really well, and we've created something from nothing, which is the coolest thing about all of this. You know, so if you've got an idea, you know, that you know, a building or something that you want to capture, you know, go ahead, and you've got a drone, be it a mini drone, be it even, you know, the original Mavic Mini, or you know, an old school like Mavic 2 or something like that. You know, go ahead, and capture some data, download a trial version of Agisoft, or you know, whatever other photogrammetry software you want to play around with, and print it. You know, it's a really fun, rewarding little process. And you know, my thing now when I'm going to go traveling is, yeah, every place I go, I'm going to find one spot that I'm going to 3D print, and you know, that's going to be my little holiday memento, shall we speak. So you know, all in all, it's been a really awesome little project, and I hope you guys have enjoyed yourself. And yeah, please let me know in the comments what you think. And you know, if you have enjoyed it, then yeah, please like and subscribe, because you know, we're going to do a lot more of this sort of stuff, and it's going to be pretty cool. So hey, I'll see you in the next one.